Okay, good morning. This is our last day, and we'll start with the almost last speaker, Nani de Micheli from EPFL. Nani did his graduate studies here at Berkeley, and he came first to Berkeley in 1979, right? And yesterday, Nani told us that he wants to take us to a fabulous restaurant, which is the first restaurant that he ate in Berkeley in 1979. So we all walked to the restaurant, and we saw a big sign, restaurant and saloon. And we entered the restaurant, and it was dark, and it looked like a bar. And we said, okay, we are coming for dinner. And they said, we don't serve food. So apparently, for restaurants, it's not a good business model if a customer comes to eat every 45 years.
But we did drink moderately. So. Okay, digital design, some of the challenges, the relation to EDA. This talk has a kind of a short introduction. They may overlap with the talks given before during this week, and then has a part that actually focuses on EDA and logic synthesis. So this is the bay. That's lovely. This is our bay. It's a lake. This is the campus of EPFL. And if you go a little bit farther from there, there's the International Olympic Committee. I show this picture here because I like the circles, the 5 circles, and the motto, Citius Altius Fortius, and this motto was actually extended 3 years ago by a vote of the International Olympic Committee adding communiter, that is, together. And I like it because it relates back to what we do, systems on chip. What we want to do is we want to have faster chip, higher performance. We want to have higher chips that's going into the 3rd dimension. We want to make them stronger, so basically more resilient, or actually even doing effort with less energy. And communiter means doing it together, integrating. And you know very well that all large teams are split over various cities, and they have to work together on various parts of these mega chips that then have to be pulled together. And that's challenging. Typically, the challenge comes in when you start actually piecing together the parts of a big architecture. Now, looking more globally, the challenges of this decade, and this is our planet. And there's less and less water, there's more and more CO2. And that is confronted with what we do it and the madness that we have today for AI, for data-driven systems that actually require fairly large stations, very large groups of computers for doing computation. The market is driven by AI, ML applications, and the energy that goes into that. It's huge, actually contrasts with the, I would say, the restriction that we should have in wasting energy just to save the planet. So the issue is, how do we rethink of architecture, circuit devices? So once we reduce the energy consumption, second, we can bring some of these techniques to the edge devices. An example, this is a plant by Constellation. It's reactor 1 of 3 Mile Island that actually being refurbished and ready to go just to feed one data center by Microsoft. There's another one by Google that's a data center by Google fully powered by a nuclear reactor. There's nothing special about the nuclear reactor, but just the idea that the energy that the reactor can produce would fit very well the energy that a data center would consume, and therefore putting in close proximity makes sense. There are therefore lots of issues related to deploying AI, ML data centers. Actually now the current problem with data centers is where to put them, having the density of energy that you need. And of course the various type. I just put this plug because last week Switzerland opened this Aperture system, which is a new multilingual LLM, and that's available, and we'll see whether it will have success or not. But trying to be more quantitative, we have this growing computing and data storage means. I look at the data centers, they account for about 50 gigawatt in 2025, and there's this 15% yearly growth. So somehow all the efforts that we did in cities, for example, to remove standard lights and put LEDs, in homes by using equipment which is actually very savvy of energy saving and so on, is going to be washed away by this tremendous need taken by the large computing center. And also we are facing this skyrocketing cost of sub-nano fabrication, the fabs that TSMC is going to build in Arizona, where it's one of three, were around 15 billion USD. That's a large amount of money, and when amount of money are so large, you often doubt whether they will eventually be finished in time and be fully operational. And for this reason, we need to keep an eye on what are alternative solutions. Not everything has to be done with the same style. Here you can see some technologies that can be useful for us. So you see some CNTs, carbon nanotubes in an array. This done by Max Schuller here at MIT. Hybrids like having PCM on top of silicon to do computing in memory. That's IBM, and that's another chip that actually does matrix vector multiplication with optics. And of course, that is a very important component, very useful for ML. Now, the question is that we have so many requirements, so what are the directions? On one side, you see the people who do materials, they get excited about new devices, they try to bring new devices to maturity. But we have to explore from the top is where can we go with the technologies in order to solve these kind of contradictions on the roadmap. And one solution, of course, goes back to the famous sentence by Feynman, there's plenty of space at the bottom, so you immediately guess what it's meant by the bottom. The bottom is quantum computing, because in quantum computing you assume that the elementary element is just an electrode that could be in the ground state, could be in an excited state, or could be in a blend of these states, therefore supporting the notion of superposition in the computation. And these machines are fairly expensive and complicated. There's not a single technology that actually is shown to be the best. You can do with superconductors, you can do it with quantum dots, you can do it in optics. And it is clear that the quantum computing technology will be successful in some domain, but not in all domains. It's something that we have to be very clear, because when people go and ask for a lot of money on quantum, one has to consider the boundary conditions. In my view, and you can quote me, I will get then the shots. Quantum computing goes very well in the domains of physics and chemistry, and it's successful for two reasons. First, these people build up large-scale experiments, and the computer, which looks like an experiment, actually it's a part of that. Maybe it's only 1% of the budget. And they're happy we're talking about the same culture. Mathematically, they try to find out states, conditions for molecules or atoms, solving out states of Hamiltonian. A quantum computing also is expressed in terms of Hamiltonian. So you have to transform Hamiltonian problems into Hamiltonian mechanisms that then will give you the solution. You are more or less in the same park, and this actually does work. You don't need to have absolute precision, but you can have actually good results. Things look different if you say, oh, I don't care about the stuff, I care about traveling salesman, I want to have something that solves exactly this problem. Now you have to be exact to the very last bit. These machines actually have a lot of noise, and that's why today we say that we are in the noise intermediate quantum computing area. We are transitioning to the fault-tolerant quantum computing, but this transition is long because to correct one qubit, you need many qubit, meaning that 100 to 1,000. And so the things get even more complex, and we're absolutely not there yet. The other thing that we have to put in perspective is what we want to do with quantum computers. Are they just going to be used by the Amazons, the Googles, as just in server farms to solve specific problems? That makes a lot of sense. For problems that we map well on QC, you send them on the web, and you will get them solved by quantum computing. But is there a way to bring them to the workplace, to the home, to edge devices? That's a very long road, and I don't know how much one can pursue that. And coming back to the idea of the servers, talking to my friends at Microsoft, they have on Azure quantum computers, and they have other type of computer. People are asked to try to put their programs on quantum computers. If they don't work well there, they will put it on other servers. So basically they have like, I would say they have cars with spare tires, and they can go on the spare tire if the computation is not efficient enough. Which, on the other hand, it's a way to start getting people used to this type of computation. One has to keep in mind also that when one talks about quantum computing, there are really two phases in there. There is the physical world, in which you have matter that does the computation using superposition and entanglement, and then there's the world above, the computational world, the world in which you map problems into executable. So there's a lot of effort that has to go into designing algorithms and compiling them onto the quantum substrate. So there are lots of similarities to computers. There's the kind of an instruction set that separates the hardware from the software. Here the instruction set is represented by the quantum circuits. And quantum circuits, it's an unfortunate name. It's basically kind of assembly code for this type of computers. But I'm an EDA person. I think that EDA can be extremely useful in both tasks for the creation of the quantum substrate, because placement, routing, connection is extremely important in there. For example, you want to have devices that get entangled, you have to place them close by. And then the entire process of compiling onto a quantum processor has resemblance to high-level synthesis. And we heard many things about high-level synthesis. Resemblances. Many things are different. Let me change the topic. The bottom is complicated, so why don't we go to the top? There's plenty of space at the top. What? Well, this picture relates to a project that is in Germany. You take basically advanced silicon, even though not super advanced silicon, like 18 nanometer type. And then you actually study what you can put in the BOL, back end of the line. There are lots of things that can be put there. You can put memristors, you can put RAMs, resistive RAMs, you can put ferroelectric devices. So there's another type of coprocessor actually that can be designed in close proximity with the silicon. And clearly this also leads to a kind of deep thought about what do I put on one layer, what do I put on the other layer. Apparently it's easier to do computation on the silicon than doing storage up or doing sensing up, but there is actually no rule. All this is kind of too new. And of course here you see various implementation of 3D integration. Is actually an older picture by Perrin Batu that Leti, who was building transistors on top of each other. This actually is fairly recent. You know, people use chiplet, and again in chiplet the idea is that you split a system into subsystems that you realize separately and then you put on top of each other. You get smaller chips, they end up costing less, they can tend to be replaceable. So this is actually a business trick to make the extension of the Moore law. There's also plenty of space in the cold, and people have not explored too much the space in the cold. This is the Arctic Ocean, and the first thing that was done years ago and still was never implemented successfully, was to bring down CMOS to the 79 Kelvin. You have much better performance of CMOS, and you can have advanced machine, less power consumption, less higher performance. But what I really want to talk is about superconducting device. This is an area that started, that's not really moving that fast. Interesting enough, it's a technology that started in Russia and with a big backing of many physicists. The idea is that if you want to do something fast, first you have to get rid of the wire delays. The wire delay dominate, so you go down close to the 0 Kelvin. 4 Kelvin are just enough, and your wires are in the superconducting domain. The resistance on the wire is 0. You don't have the delay of the wires. You can afford having longer wires. The second thing is that you can have devices that actually operate in terms of pulses. Now, because of the quantization of the magnetic field in the superconducting domain, if you send pulses like this, pulses will have specific shapes. And there will be actually a multiple of the basic one that has basically 2 millivolt per picosecond. That's the area under the curve. Actually, this corresponds to a flux of, again, 2 times 10 to the minus 15 Weber. And the idea that you have these objects for transfer information is very powerful because it's very lean. If you have a logical one, you use a pulse. If you don't have a logical one, you don't send a pulse. And then you do all your computation based on that. The pioneer on this was Likarev. He developed that in Moscow, then he moved on to the east coast of the United States, and he actually has been growing a fairly large group of people who actually work on this. The design style, well, this is basically a classic computing paradigm that has deep pipeline logic, and there are many variants of this, including adiabatic computation. So you don't need to have all those techniques that are needed for quantum. This is much closer to the regular sequential design. These are chips done, and this is one in the adiabatic domain. This work on the adiabatic is mainly done in Japan at Yokohama National University by the group of Yoshikawa-san, and also he has a lot of people with him. Now, the interesting thing here, the pointer is this. What's happening? I have to go backward. Interesting thing here is this table that shows various embodiments of this technology. And one has to look at this column here, which is the area delay product. And the various technologies that uses in a natural way superconductors are in this range of EDP, which is much better than CMOS, but the adiabatic version has a very small consumption of power. So this actually can be seen as a way of doing very low power devices. So in summary, you would use superconducting electronics as support for ultra-fast acceleration, for example, in the case of ML. It doesn't make sense to make small chips because you need to cool them, so you need to amortize the coolant. You need to build big things to be significant. Low power operation, but the low power operation is limited to the fact that you have to refrigerate, so your refrigerator is the major pain in the neck for the energy consumption. This technology also works very well as a bridge to quantum computers because quantum computer parts operate in the order of tens of hundreds of millikelvin. So they have to be very cold because of noise. And then you interface to CMOS. And so there's a big delta in temperature. And remember that once you have wires, the wires carry very well electricity, but also heat. And so you can make intermediate stages done with this technology that can be good, for example, for doing error correction or control of the qubits. But there is a big need of EDA tool in this domain. There is not much space in the hot. This is a picture of Dalí with fire in Barcelona. And the heat is actually the showstopper for many things. It's the thermodynamics of computing system is the limiting factor. When I go and see our experimental data center at EPFL, the first thing I see is the pipes of cold water that come in and the one of warm water that go out. This is what actually dominates, and the pipes are much bigger than the chips and all that. One has to think carefully if some other thermodynamic principle can help in making the computation more efficient. I'm talking about reversibility and adiabatic computing. There's not a clear answer there. I will elaborate on this in a minute. But what is clear is that computing systems that we use today are still very far from being efficient. They are very inefficient. There's lots of heat that's generated that it shouldn't be. And when we scale the system up, we should be able to make the systems much more safe. So I mentioned the thermodynamic. In thermodynamics, we know that if you have a reversible process, that is more efficient than an irreversible one. And you see here you have a heater or a heat pump. These devices now are used all over, also to heat the house or cool down, and nobody uses the spiral where just you create heat by just having current going through some resistance. Now, quantum computing uses reversible electronics and reversible logic. But that is not by choice. That is the fact that we don't have gates that actually do the quantum computation. We have matter doing it. So some matter on the quantum chip gets stimulated, and then some signals bounce back. And by analyzing this, you have basically the reply of the gate. And that's the nature. And that is reversible because nature itself is reversible. You give the output, you get back the input on that type of experiments. There is some attempt to build circuits that are reversible. And there is also a very fine line between reversible and adiabatic. In adiabatic, you say its process is adiabatic if it has no exchange with the exterior, no heat exchange with the exterior. So the classic way of showing an adiabatic cycle is in the turbojet of a plane, because everything that is quick in thermodynamics is adiabatic. The air comes in, gets quickly compressed, that gets heated, and it goes out, and the plane goes ahead. But this is not the same thing in electronics. Electronics actually is quite different. There's been a lot of work 20 years ago on adiabatic computing in CMOS. The idea was that you have to charge capacitors in a CMOS chip. As you charge the capacitor, some energy is dissipated. But if you can make sure that the voltage drop is small during the charge, then the energy is much less than the typical one given by the formula 1/2 CV squared that we all know. So that actually was never really shown in practice to be successful, because in order to make that work, in order to have the clocks that actually vary, then you need too many transistors. And at some point, you waste what you gain. In adiabatic computing in superconducting electronics, the keyword is AQFP, that's what's done in Japan. They do a dual thing. They charge and discharge inductor of a very small delta I. and they manage to be adiabatic. Some example, that's a Toffoli gate using quantum computing. That's reversible. From the output you can get to the input. Remember that typically the number of inputs is less, so as soon as you have more inputs, that you have more complexity. And in the end, this is a permutation. There is a company in Britain, Veyer Computing, that actually is trying to build a reversible adiabatic computer. And they use this notion that energy should not be wasted, but should be recycled. So their chip consists of two parts, an inductor and a chip. The inductor is the L, the computer is the chip. So energy goes from L to the chip to do the computation, and somehow the excess is recycled back as bringing back the L charged. And then you can go through another cycle. Okay, that's the idea. I'm not sure if they're going to be successful at all. It's just hard to predict. These actually are the chips by Yoshikawa in Japan. Actually, they are interesting because they have two superconducting loops, and typically one has a flux through it, and the other one doesn't have a flux to it. And the clock goes over these spirals there. When the clock passes by, it basically makes everything very sensitive. And if some current comes in from here, has to go this way, and so we'll turn on this JJ, and then you will have a flux here and not here. And so you will have a switch going from here to here. When in presence of the clock, you will have a small current pulse coming through. And so that's how you define the logic state 1 and 0. And then what is nice that this thing can be modularized. Those circuits can be seen as buffer, and you actually can connect 3 of them or 5 of them or 7 of them and make a majority gate. And that can be used for doing the building blocks for logic. So first part of my talk, the key point, it's important to remember diversity of architectures and devices. We have to keep on looking at what we can leverage from emerging technologies, and we need to have computational models. We may use alternative technologies to do accelerator for some specific function. What we know is we use FPGA as an alternative technology today, but it's still CMOS. Things can be more radical in the future by using something of different nature. And indeed, the whole premise of quantum computing is to have a quantum computer as a coprocessor for specific tasks. I think that's as far as it can be, and it could be extremely useful, but just a coprocessor. And what you need in order to have diversity? Well, you need to have new computational thinking model, and then you have to adapt, create new EDA tools and chain. The EDA is still not there for all these type of things. So in the second part of my talk, I want to talk about EDA for emerging technologies and paradigms. So this is a nice historic picture of a Kalmar workstation that existed when I was a child. And I didn't use it. I was just going to a regular school for children. So things evolved a lot in electronic design automation, and many steps actually have gone ahead. Want to see what are the major problems? I will list a few, have a small comments, and then zoom into an area where I'm an expert that I want to give you a flash of what is present today. You want to have accelerators, accelerator for different parameters, and therefore you want to have high-level synthesis. That's an important topic. We have validated that this topic is important during this week. We want to have correct simultaneous computational units and chiplets connecting the whole thing. That's network and chip. The technology is there. Arteria is actually selling very good tools for doing that. Problems do always exist because things can be complicated. But in the end, what you want is to kind of leave the NOC the advantage of gluing together parts that can be various in nature. you want to synthesize computational elements that are secure. This is extremely important. And so you need to extend logic synthesis to support, for example, encryption methods. And then you want to perform physical design for PPA, power performance area, and you want to support a variety of backends. So what about high-level synthesis? Just one slide. These are high-level towers that you see there. That's in Italy. And for now, you know, HLS is a reality, principally for FPGA, but also for ASICs. We have synthesis from HDLs and C-based model. But the key thing is to be able to address the possibility of putting backends on different substrates. And that's what is not there yet, and that is very important. I have a system, maybe it's already been designed. I have all the HTL, and it's already and always been implemented in CMOS, and I'm saying, hey, I talked to Subhashish and to Mac, and I have this building blocks done with carbon nanotubes. It would be the time to use these parts as accelerators. How do I fit them in? And here I'm not talking about the physical design complexity of joining two technologies. The ability of reasoning with part of the chip that will respond differently. Probably this part would be faster, and so they will completely unravel the series parallel structure that we had before with only CMOS, and so on. So it's very important to evaluate technology choices at the high level when we know that the target is different. And then, of course, once you can do it with various models, you have even more of a variety of choices because your design space gets even bigger, and then leverage AI/ML to do the exploration of the design space. But I think that these two things should be together. Being able to explore better and be able to vary the menu of the components that you can have. As far as the NOC is concerned, this, I credit Federico Angiolini for this picture here. NOC, you can see there are elements that are written down by these blocks, these ovals, that they communicate to the others via packets, and the packets go through some switches or routers. There's a sketch of a NOC. The main reason for a NOC is scalability, because already above 5 to 10 elements, it's very difficult to connect them through buses. And the idea that with a NOC you can tune power, frequency, area, you can stop a block, you can speed up a block, blocks go on different islands that can have different frequency of operation, different voltage, and the NOC does all the dirty jobs of connecting, including the fact of buffering information that comes in that cannot be absorbed, and so on. And the end result of a NOC is to ease design closure. I think that's the biggest selling point of having tools that implemented NOCs, because you lead typically to fewer, shorter wires. You have a decentralized control of the communication scheme, and then you can really incorporate various parts in an harmonious way while looking at the constraints of the different components that you have. Now, logic synthesis, so that's my favorite, so we'll spend more time on this and start with this slide. That is, there's still tomorrow for logic synthesis. There was a very good Italian movie, There's Still Tomorrow. I don't know if anybody has seen it. The key of the story was in '46 when women were given the right to vote for the first time, and when many men didn't like the idea that women could vote because probably they would oppose their wishes. And so there was this woman who actually really her dream was to go and vote, and because of many reasons she couldn't go to vote. But in Italy you can vote on Sunday and Monday morning. So there was still a tomorrow for her to vote. And movie was quite nice, but I want to stress, there is still tomorrow, there are many things that can be done in logic synthesis, because sometimes when they ask me what you do logic synthesis, then they look at me and say, oh, right, this guy has a jacket, has a tie, he belongs to last century, and now we're just wasting our time in listening to him, All these problems are solved, and there are these two companies, which I wouldn't name, they always say that they solve all the problems. That's just you need to pay, but they will solve all your logic design problems. Well, the reality is that the main fabrics of chips are just networks of gates. You have them all over. And we know a lot about logic networks and synthesis, but one way to know a lot is not to look at our classical text or talk to the vendors or talk to people like me, but go back to the source, Donald, the good Donald. In this book, he has found out so many amazing things about algorithms, and I think he did it mainly on his own. So I have a lot of respect for Donald Knuth's book on synthesis. And the reality is there are more things that we do not know as compared to things that we do know. It's like the black side of the moon. But then people come up to me and says, is that relevant? We have this, all the blocks that we have get compiled by tool XYZ, and we have reasonable PPA. We are very happy with that. We can, maybe our problems are somewhere else. There's no need for an improvement there. This is not actually true, because all of them, they want to squish out 1% of area, or there's always a desire to do something better. So problems are not really solved. And there are new things. This actually was a citation on Knuth's book when I started working on majority. We started working on majority logic years ago, and then we find in the books that said majority is probably the most important ternary function in the entire universe. Donald thinks global, because it has amazing properties that are continuously being discovered and rediscovered. So he already knows, Donald Knuth, that we know a lot about majority, but there will be something else to come. So that was fairly comforting. And by the way, people have been doing majority logic in the 50s and in the 60s to do adders and multipliers, but never studied systematically the property of majority for doing random logic and doing anything else than adders and multipliers. So what it is, majority, obviously you have a group of people, got to be odd, and then you count how many say yes, and it's yes if the majority says yes. So this can actually captured by a set of axioms. These axioms actually come quite easily from medium algebras, but these axioms actually represent a set which is sound and complete, which also gives the reachability property, which is something important. You have a circuit, imagine, and you have a configuration, and it's here. And then ideally, there is the best configuration that it's there, faster, smaller. Is there a path by doing simple changes that will take me from here to there? Yes, according to this, you can have a path. There are other models for logic that are not reachable, so you can be stuck already by definition into that. Reality is that the existence of a path that leads you to the global optimum is something that helps you very little, because this path can be of a number of exponential steps, or it's something that you don't find it. It's there, you cannot find it because you're not smart enough. So, but at least in principle, you can get to the optimum. So that's good. And then in the end, what you do, you create graphs. This is example to make them simple. You have nodes that are 3 input majorities. You have inversions as bullets there. And that's how you represent your logic. Then what you do logic in terms of majority inverter graphs, MIGs. And then you have 2 major ways of optimizing them. One is to create a set of rules for rewriting these graphs. The rules come from the axioms and come from combining the axioms in various ways. So here you have one structure, and here you have another structure. Doesn't look that different, but some of the variables do change. The bubbles appear, some signals may be available earlier than some others, so all this is useful. Or you can use Boolean methods for majority that actually exploit the fact that there is some sort of redundancy in majority. So suppose that here you're doing a majority decision, and here you would have some subnetworks. Suppose that these have some errors because you simplify the network, and so they are not complete, they give something wrong. This error may be corrected by the third part. And what I'm saying here informally becomes a set of constraints that can be applied so that whenever you have a node and you look at the transitive fan-in, you have rules on how you can optimize the various parts without violating the result in the end. So in the end, what comes out? We worked on this between 2015 and 2020 on doing majority for CMOS. And we found out that we could speed up in the end circuits, but about 15% or less, all the rest being equal. So that's been a nice result. This was done on our tools, and also it's been done on the tools of a major company that actually sells software, that they found that this is interesting. And then what's interesting is that this technology can be used for superconducting electronics, can be used for optics, everything that's based on optics where you have waves, because these waves actually interact. So they sum and they subtract. And so majority, again, plays the game. And now with Pierre Emmanuel, we found a way to use it on a particular structure for logic in memory. Then, of course, you said, well, why majority? Because we picked up majority, it looked good, and we use it, it's good. But going to majority means also forgetting the simplest model when you do logic, which is 2-input NORs and NANDs, and going to a 3-input gate. But what about other 3-input gates? How many are there? And how many 3-input gates actually can be used, and how many of them are equivalent modulo NPN, negation of the inputs, that is complementation, P permutation, and negation. So if you look at that, among 3-input gates, there are only 10 that are of interest, and they range from the N3 to the XOR 3. But the XOR 3 is just a linear gate. That's not complete. So you cannot make, so this you have to throw it away. And now you have 9 candidates. And so what you do is, well, you do an experiment. And again, this experiment doesn't have any general validity. The experiment was taking 6 input and 6 input function and synthesize them by using one of that primitive, using exact methods, using SAT. So you get the best. And that's the surprise that you get this gate here that looks a little bit an ugly duckling here. And it has the midterm like this that we call dot, that actually is the best in implementing those functions. Why? No intuition. Would this extend up to function that has 7, 8, 9? Sorry, I cannot do it because that would take too much energy, or maybe I will be done in the year 3000 once that will finish. So, but that to tell you again, that in logic there are many things that we do not master, because making blocks with 8 inputs is something that we should be able to design exactly and well, and we don't know. Next, a few more consideration. We actually spend some time in thinking, how does logic function come together by having a linear and a non-linear part. The non-linear part is related to the ANDs, and the ORs, the linear part, related to the exclusive OR. And keep in mind that the exclusive OR is always being considered a bad guy because it doesn't come out well in CMOS. So AND logic is nonlinear, majority invert logic is not linear. This is an AIG. And inverters, this is majority inverters. You don't see the inverters, but these are the edges that are actually dashed. And the last one is an XOR majority graph that's more compact. Of course, that's an example, so that's a good picture to put there. But indeed, if you do with XOR, you actually find some very interesting properties. So it is sometimes interesting taking a network to decompose it into the linear and the nonlinear part. And this brings up to these graphs that are actually the XMGs, that are XOR majority graphs. And you have two operators, the majority gate, 3-input gate, and the XOR. And both functions are self-dual. That is, if you complement the inputs, the output comes up complemented, and have this very interesting property that spatially you can commute this gate. This is equivalent to that because you are putting the majority at the bottom, and then you do the XORs. So there are many things that can be done in optimization by shifting things around, considering the fact that in real circuits you have inputs coming in at different type. So the late inputs, you want to shift them in a place which is closer to the output to make the circuit more perform. And this was also something that we discovered more or less by accident. The way in which we discovered is that for years we worked on devices based on nanowires that had two types of gates. One gate determines the polarity, that is the fact that the transistor is P or N, and the other one determines whether the transistor is on or off. Well, once that is done and things look like this, actually not really, silicon is gray, it's very boring, this is being color, Photoshop does the task. But then you could get actually this construct that this transistor, the arrow in here is the one that tells you whether this is complemented or not complemented. So this can be a P or an N transistor. But by arranging two pairs, you could do the 2-input XOR, the 3-input XOR, and the majority. So somehow, using that technology, then you could use building gates that are fairly interesting. And says, okay, that's very nice. So we should look at libraries that are abstractions of these blocks and see how we can map large circuit into that, because then we know how to implement it with this. What happened then? Two things. This is very nice. But even though you build in the fab things like this, as a university, it's very difficult, you have to say to the world, you use my fab to do this funny transistor. So this was the sad part of the story. The good part of the story is that you get a model in which you have majority and XORs. You get tools that map this that can work very well on CMOS and do much better than other techniques. So eventually, as a byproduct, you go back home and find that these techniques, just because they exploited new ways of thinking, new ways of doing it, actually bring back results that are useful. And I like to show this with this circle of innovation. You start with CMOS, which is an established technology. You bring in a new technology. You develop EDA for this new technology. And eventually, you apply this new EDA on the CMOS, and you get some change. And actually, here I show the Phoenix, the bird actually that comes after the senders. And this actually has two messages. One, that one has to be broad and actually look beyond the principle, the constraint of a technology. And the second, that today, at the level in which we are with Moore's law, we have really to look at what are the other connection possibilities that you can do with your technologies. There are some, and this is something that came out over the last 5 years. Now, a couple more things. The multiplicative complexity. So now we change our graph. As you understand, my game is to build graphs that have as node some particular primitives and looking at various of these graphs and looking at the properties. So now I want to use an XOR n graph. I take away the majority. Why? Because I want to have on one side the linear part, XOR, and the end, which is the nonlinear. And then we can look at XOR n as the abstraction of the arithmetic operations, that's basically addition and multiplication. And the advantage of doing this type of separation. It turns out that it's very important to be able to compute how many n's you need in order to build a function. And this is called multiplicative complexity, MC. If you have a function, you can have many implementations. So out of this many implementation, the one that has the least number of n's is the one that defines this multiplicative complexity. But also, this property is fairly interesting. And keep in mind that reducing the MC means reducing the nonlinearity of the circuit. One would say, can we get rid of the nonlinearity? No, sorry. If the circuits are fully linear, you can implement some blocks, but again, that's not general. If you build adders, you need to have at least 1 to n gate per bit in order to make it work. You can try whatever, but if you don't have that bit of nonlinearity, you cannot make it. Now, how can you compute this? As any important and interesting problem, the problem of finding MC is NP complete, and it's known only for a limited number of functions, a function up to 6 input that's being tabulated, and it's known. By the way, there's also the notion of multiplicative depth, which is the longest path of n gates. So here you'll see actually how you can compute the MC. If you take a function, and now as an example we take the majority tree, and the structural multiplicative complexity is the number of n that you will have in an implementation. But this is not really the MC, because the MC is over all possible implementation. Actually, there is one implementation of the majority function that uses only one n, and so the MC is equal to 1. So why do I care? It's interesting, these problems were brought to us by people at NIST, that start looking in, and you can spend a lot of time in doing theory, but at some point we wanted to look at some applications. These are 4 applications that we found very interesting. One is reducing this MC. It's good to synthesize circuits that are robust to side channel attacks. The second is that you can optimize quantum compilation by minimizing the number of T-gates. I have to explain a little bit more on that. You have a computational flow, and you have it as a graph, and eventually you want to map it to the quantum circuits of your quantum library that implement this flow on the quantum computer. The typical gates are like either CIN or the Hadamard, but in order to be complete, you typically need to use this T-gate, which is a rotation of pi over 4 on the block sphere. Well, this is the bad guy. It costs more. It's like a gate that is big. But it's not a gate that's big, because we're talking about quantum. So what happens, in order to implement this rotation, you need more time, because you need to have more pulses and check done on your material. So there's a cost that's higher. You want to minimize it. Well, it turns out that you can manipulate your quantum circuits during logic synthesis. And you can use some intermediate gates like the Toffoli gates. But if you reduce the multiplicative complexity, then you would reduce also modular number of 4, the number of T-gates that will appear in there. As a result, what you do, you get some code that will run faster on your quantum computing, which is a good thing. It's not the only way to speed up the code, but actually reducing number of T gates is something that people like. Another application that's different, it's in the garbled circuit. Here I don't want to get into more details, otherwise I will go far away. But the garbled circuit protocol is one protocol for privacy-preserving communication, was invented by Andrew Yao. And it's, for example, there to solve the millionaire problem. There are two millionaires who actually meet, and they want to figure out who's the richest, but nobody wants to say exactly how much money they have. And so they start passing information in encrypted form, and finally, they get to the answer who is the richest. And the protocol requires a lot of transfer of information. So if you want to use this to secure information, for example, on a watch, the communication will be too long. So part of speeding that up is creating a protocol that uses primitives that are limited, and again, that relates to minimizing the number of ends of nonlinearity into that. And finally, another one is improving efficiency of computation in FHE, fully homomorphic computing, in which you do computation with data that is encrypted, so nobody cares about stealing encrypted data because you cannot read it. But still, you want to make that in an efficient way. So my point in all this, all these problems are fairly interesting. So what we do as part of our research, we work on algorithms, heuristic algorithms that bring down the MCs in various graph representation. And by doing this, we have impacts in these various areas. In particular, if you look at FHE, I just said you compute functions using encrypted data. And if it's encrypted, it's more complicated, so speed becomes a concern. And so what you do is you want to use logic synthesis to restructure the computation. And here you have to be careful, because in FHE, you compute with addition and multiplications, and you have some noise. And this noise actually masks the data so that actually the bad guy cannot find out what you're doing. But you have to keep some noise, but then the noise goes up, and actually goes up quadratically when you have multipliers. And if the noise becomes too much, then you lose track. You cannot actually recover it. It becomes too difficult. So what you need to do is to be able to, this operation that are called bootstrap, at some point you will kind of reset, get rid of some noise, can re-extract the real data, but not make it completely unclear because you want to keep it hidden. But of course, all these operations of bootstraps are operations that cost in terms of circuit, cost in terms of performance and area. And again, using various models, one is actually using this kind of objective function in which you deal with the multiplication depth, because you don't want multipliers feeding multipliers on a path. And this is the complexity, number of multipliers per se. Using this as a driver, you can actually simplify the circuit to get the skeleton of the computation so that it's more efficient. Another interesting thing that it's come from a different path, it's a technique that's been around, is balancing circuit by just doing balanced XOR decompositions, and that's helpful. Other thoughts, quickly. Pipeline in logic synthesis. You have to know where insert this bootstrap. It basically can look at a computation as a pipeline. You can use kind of retiming-like techniques to minimize the number of bootstraps to be inserted. And that actually helps in doing the distribution. Coming back to pipeline in SC circuits, the circuit that we were talking before have various features. This is a classic CMOS, and this is a SFQ implementation. And here you see two things. You have to buffer out a fork because you deal with these pulses that are so small, so you cannot have a fan out of 2. And here you have to align the data, because all your computation is done by these pulses that go, and you have to evaluate when they're aligned. You cannot actually end 2 pulses. One is here, one is here in time, because otherwise you would actually, if data is misaligned, you don't get the right computation. And so here you see how the data actually would flow through to get something right. And so you have to insert these buffers and these splitters, and this becomes an interesting problem. This is just a full add, and in full out you see that there's a point here where you have a multiple fan out, so you have to put in a splitter, but then a splitter unbalances the circuit, so you have to put in some buffers, and then you end up with something like this. So from something small you can end up with something complicated. And you have to be careful, because already you have an overhead, but if the overhead is too much, then it will kill you. So techniques that we use now is that actually we look at this legalization as scheduling, and once we have a schedule for the operation of the gates, we can find out what is the best way of inserting these splitters, and then which we can do it in polynomial time, but finding a schedule it's much more difficult. So I'll go quickly on this. Physical design, that's not my area. It's a multiverse. There are many things happening, especially if you look at new implementations like issues where you have planarity, you have wire crossing. This is all field-connected devices, nanomagnetics. You have the problem with 3D integration where the delays are not isotropic, and in superconducting electronic, one of the issues is, again, clock. And so most likely for any technology, physical design will be the showstopper at some point. It will be too difficult to do it. Looking at the future, the elephant in the technology room, that's me and Srinivas Murali on an elephant. And what's the role of AI, machine learning? Well, you can apply it almost everywhere, so I will see a complete revolution in terms of EDA, but I think design space exploration is the main part. Key point number 2, EDA is enabler for future computing. AI application will require better chip. Theory and practice of EDA actually are the ones who are necessary for its evolution, and synthesis will actually the means to get designs that go beyond PPA. And of course, verification will be even more essential as we bring in AI technologies. And let me do one thing. I have a few more minutes. Just moving away from technology and closing with some parting thoughts that I feel I have to say. This is Konosuke Matsushita. He was the founder of Matsushita and Panasonic, and his motto was peace and progress through prosperity. Peace and happiness through prosperity. This was changed into peace and progress through prosperity, and the 3 terms have a circular dependence. That's very easy to understand it. I like to extrapolate on this and put the key point number 3 of my talk is progress through peace and prosperity. We cannot have progress if we do not have peace and if we do not have prosperity. And any major improvement in computing systems requires a large effort. That's what is needed in order to have progress. And about peace, cooperation is essential to be able to pool exceptional talent and fabrication technology. We have the best people all around the world. We cannot actually discriminate on the basis of race, national identity. And we also need to have bigger market and volume in order to have new applications to succeed. And eventually prosperity. This is very valid in Europe. We need to support and retain engineers with good rewards. Sometimes rewards are not good enough, and engineers run out of that. And we have to keep enthusiasm and freedom to explore new directions, and actually to empower engineers to be successful. In conclusion, Efficient computing needs a matching between architecture and technologies. Accelerators play a key role. Logic modeling and logic reasoning is a fundamental tool. The algorithms can be applied to the established technologies as well as the upcoming ones. So logic synthesis is the key to understand how new technologies can be useful for computation. And chip design is entering a new epoch with AI, ML, and we need chips to sustain the fast execution of algorithms, software, and services. I'd like to thank you. I'd like to thank the sponsors, and I'd like to thank some of my students here at Stanford. Subhashish, you are in there. That's you're not formally my students, but we collaborated in the past a lot. And so thanks to them for what I'm presenting to you.
Questions?
Yes.
So thank you for a very interesting talk. The first half hour or so was about alternative technologies, but the remaining part, which was about EDA, seemed to focus primarily on standard logics. Is there an expectation that these alternative technologies will also would map onto standard logic? I mean, I understand majority is a different function, but it's essentially still a part of basic logic, of traditional logic. Are there fundamental new problems in the EDA space that?
Oh, yes. I think there was a link. For example, you take superconducting electronics, you have to be able to design pipeline logic. And you have to make it efficient by playing with the two knobs that are the splitter for fan-out, so fan-out based synthesis, and with the buffer, which is, again, can be seen as the retiming effect in order to keep everything in line. If you look at quantum computing, you do need a lot to use logic synthesis for realizing the oracles, these blocks that we compute combinational logic within quantum algorithms. And there you will have first one important set of techniques, which is the reversible logic synthesis, because the logic has to be resynthesized in a reversible way. And second, you have building blocks that are of different cost. And you cannot really use the classic technology mapping blocks, also because these elements are typically multi-output. And some cells are much more expensive than the others, so the chasing of the T cells is a very important thing, and reducing them is very important. Besides, I think it's very important in the case of quantum to be able to have a set of logic synthesis tools that can be adapted, because for quantum, we don't know what the final technology is. We are experimenting many things, and Microsoft came up with these Majorana particles and all this, then the paper was retracted, or almost retracted. So we don't know whether that's a path or not. It will take probably years to figure out what's the best. And more or less it's going to be the same, but then the relative cost of the components may change. And that's why you don't need to have a kind of hardware solution, but you need to have tools in which you can play with the parameters. So I think that really all the synthesis kind of intertwine with the technology. Both the synthesis and, of course, the physical design. But that's extremely complicated, because change the technology, then the physical design changes abruptly. Yes, Subhashish.
I think I was just going to respond to that question. I think there are two things going on. There are certain kinds of new technologies that might have abstractions that are similar to Boolean abstractions.
That's what I got the feeling for so far. Yeah.
But even for that, there are kind of two, multiple levels of the problem, which is like, one is, so for example, if you're at a logic level, for example, you might be able to use a lot of these techniques for those abstracted situations. But once you go to one level up, more like an architecture level, then the kinds of explorations and synthesis and design that you have to look at, those could be very different than what we are used to. And I'm not trying to promote my talk, but like this whole point that I was making about 3D folding versus that sort of a thing, that's an example of if you just followed existing EDA, then you would do 3D folding, for example. So, that's an example.
Any question?
I had a question. I never studied adiabatic computing very, not to at any level of depth, but I know that, you looked at it at some point, right, in the past, Does adiabatic computing, that field require the algorithms folks to rethink their algorithms, or is it that, it's more like a, implementation question and not an algorithmic question?
I never had any contribution to adiabatic myself, but I looked at it because I was curious. The technologies on CMOS done by Marius Papaeftimio require circuits that were more complicated than normal, and that was a little bit the killer in there. If you look at the Japanese AQFP, the circular, not that simple, but I think they are fairly modular. And they don't need any specific algorithm because they implement majority. Actually, the way in which they do it, they reduce majority to ANDs and OR. And it says, I have ANDs, OR, and inverters, and then you do whatever. My point of view is, if you have majority, just don't do AND or inverter. You can do much better because you can play. But there is all this trick that these are systems that are clocked with phases and they have to overlap with phases, so they get fairly complicated in that way.
So at least for now, whatever has been done in adiabatic, it's mostly at the implementation level.
Yes.
Assuming that the software stack part of it would stay the same, roughly. Yeah. Now, an interesting question for this group would be that, clearly, adiabatic had its issues and it didn't really fly until now. Is there an opportunity to rethink at that level to make, these things more palatable? I don't know. I have no idea. This is a thought that, came to my mind.
And then I'm just looking at this by curiosity, but the way in which people use the name entropy adiabatic in thermodynamics is different than what's been used in this field. And even though there are similarities and there are all these things, when push comes to shove, things are different.
Here. Oh,
Sure.
Yeah, so I'd like to also get Nani's viewpoint about this analog computing. Yes, while we have discussed, lots of it is all applied to digital. And we all know that analog computing could have gave you quite a bit of power energy advantages. But it's not, it's only at certain applications right now. Do you think this might have a future?
Oh, yes. Yes.
And where is the bottleneck at this point? Is it EDA is the bottleneck, or still a lot?
Well, you can do analog multipliers and others, and they will consume probably much less and be faster in response. And I think the one reason why moving out was the precision. But now if this is used within learning where you can tolerate some error, you don't have to be precise, this becomes useful and interesting.
There have been papers, by Boris Morman and others, where what they did was, the way I say it, is it's digital thinking, and and then what's the right word? Selective analog implementation. So you still think of your data flow and everything just like how you would think of a digital system.
Because of the simplicity.
Not just simplicity, but even to reason about, you're not going to implement the whole thing as an giant analog block. So then, because then that would be very inefficient. So instead, you think about how you would think of a very efficient digital system to start with, and then pick certain blocks, like Nani was talking about multipliers, for example, right? And then have very efficient analog implementations of those. And if you can have enough of those implemented the right way, then you would get an energy efficiency benefit. So there was a paper by Danny Bankman, one of Boris's students. This was in ISSCC 2018, 2019, around that time frame, that actually explored some of those ideas.
All right, let's thank the speaker again.
Thank you.
Coffee break now.
What's your talk?